Okay. Alright, good morning everyone. So how's the implicit differentiation homework going? Going good? Going not so good? What's up?
It's not bad.
Okay. Any quick homework questions you want me to go over for that one? Because I know there was a lot of tricky ones on there. Okay. Alright, well, let's go ahead and get started with some related rates. Before we do that though, some announcements. Basically just the things that we talked about yesterday on Monday minus the, quiz 4 part. But aside from that, quiz 5 opens up on Friday at 9 a.m. for 24 hours. Quiz 6, I believe, opens up on, I said Wednesday, if I recall correctly.
Yeah.
Okay, just want to make sure. So Wednesday, and then the exam 2 opens up on Saturday, and you would have on Saturday, October the something. One second. Calendar opens up on the October 10th, and then closes on the 13th. Okay. All right. So, any questions on any of that? Okay. Like I said, any homework questions you want to go over real quick? Okay. All right. Well, let's go ahead and talk about some related rate stuff. So basically, we're just gonna go straight into some examples. So, like I said, the main idea of this lesson is to relate rates to changes of things or objects or whatever, using both chain rule and implicit differentiation. So lesson 15 is essentially sort of a continuation of lesson 14, essentially. Except now we have that our independent variable is t, and we have now two functions of t in this case that are differentiable. So let's take a look at example 1 to see what I mean by that. So we have x and y are two differentiable functions of time t, with 5x to the 5th times y equals 10. So x and y satisfy this relationship here. So the goal is we have to find dy dt if dx dt equals 2 and x equals 1. Okay? So here's what we're going to do. So first off, we'll say recall. So basically, I'm just going to bring back that asterisk rule that I brought up last time. So chain rule says, for f a function of x, we have f a function of x, and g a function of y. So we have that if we differentiate f with respect to t, if you recall, that's the same thing as, well, if we use our Leibniz notation, that's the same thing as saying df dx times dx dt. Okay? But a slightly different way of rewriting this, even though this is correct, is just f prime of x times dx dt. Okay? So what you'll notice is that, again, this is basically the same asterisk rule that we had last time, just with different variables and notation. But aside from that, it's basically the exact same. So just some different variables being thrown around. Okay? And then for g a function of y, it's going to be similar. So we have dg over dt equals dg, in this case, over dy, because that's our g is a function of y, times dy over dt. And so similarly, you'll get that this is g prime of y times dy dt. Okay. So, like I said, these are basically the asterisk rules that we saw from last time, but now we're seeing them with some slightly different notation. So, So the nice thing is that in general, if you have f a function of some variable which in turn is a function of t, then these asterisk rules will apply here. So, but we'll get to that in a second when we get to our text examples. So now the thing is that, like I said, we have, all right, if we have 5x to the fifth times y equals 10, then we're also given that x and y are differentiable functions of t, and we have to find dy dt if dx dt equals 2 and x equals 1. Okay? So if we use our asterisk rules given here, then we say, all right, well, that probably means since both x and y are in terms of t, we should probably use implicit differentiation, except with t as our differentiation variable. So, d over dt, 5x to the fifth times y, equals d over dt of 10. Okay? So, as I established, x and y are functions of t. Okay, so in this case we say, all right, well, we have one function of t as 5x to the fifth, and then we have another function of t as y. So what we notice is that we have 5x to the fifth times y. So if we want to differentiate this with respect to time t, what do you think we're going to need to do? What rule do you think we're ultimately going to need to use here? Product, right? So in this case, we're going to need to use product rule in terms of t. Okay? So there's that side, and then of course the right-hand side is just derivative of a constant, which is always 0. So nothing too crazy with that. Okay, so now we say, all right, so if we let f equal 5x to the fifth, then we have to say, all right, well, we ultimately want to find the derivative of this function f with respect to t. So in this case, we should probably say, all right, well, we should probably use our asterisk rules here to figure out how to do that. So in this case, we say, all right, if we differentiate f with respect to x first, because that's the first part of the asterisk rule, then what that says is that, all right, well, we have df over dx. Well, that's just a quick application of the power rule. So f prime of x equals 25x to the fourth. Okay, so now we have df dx. So then to get df over dt, well, by our asterisk rule, all we have to do is just multiply dx dt to our derivative. So we have 25x to the fourth times dx over dt. Okay? So that's ultimately the derivative of f with respect to t here. Okay? So now let's do the same thing with y. So if we let g equal y, then if we apply the same procedure that we just did here, from going from f to df dt, what would that tell you about what dg dt is? Taking the derivative of g with respect to t. Go ahead.
And it'd be just dy dt?
Yep, it's just dy dt, right? Because in this case, all we have to do is just say, all right, well, we need dg dy, or just g prime of y, which is just equal to 1 by power rule. So then dg dt is just, well, dy dt, because g prime of y is 1, so all we have to do is just multiply that to dy dt, and then that's it. So that's that part. So then that's the case. That says, all right, well, then product rule then says, all right, well, d over dt of 5x to the fifth times y is then just, well, the first function times derivative of the second. So we have 5x to the fifth times dy dt, and then plus, let's see, the second function times derivative of the first. So we have y times 25x to the fourth dx over dt. And because that equals derivative of 10, that's just going to yield 0. So let me go ahead and write that a bit more cleanly. So we have 5x to the fifth times dy over dt plus 25x to the fourth times y times dx dt equals 0. Okay? So now the thing is that we say, all right, now as per the problem statement, we ultimately need to figure out what dy dt is. So the problem says, okay, we're given that x equals 1 and dx dt equals 2. So that tells us what's going on with this, and this. But oh, wait a minute, we don't know what y is. So that's kind of unfortunate. So how do you think we're going to be able to find y in this case? Any thoughts or suggestions?
You could plug 1 in for x in the original function.
Right, so we have to say, oh, wait a minute. We already know what the original equation here is, so maybe if we plug x equals 1 back into here, maybe we could figure out what y is. So now if x equals 1, oh yeah, sorry. If x equals 1, then 5 times 1 quantities to the fifth times y equals 10. So that should pretty quickly imply that, well, in this case, y should equal 2. So now we're given we're given x equals 1, y equals 2, and dx dt equals 2. Now we can go ahead and plug them into here to figure out what dy dt is. So find dy over dt. So we have 0 equals, well, 5 times 1 to the fifth times dy over dt plus 25 times 1 to the fourth times 2 times dx dt, which is also 2. So then we have, well, 5 times 1 to the fifth, that's just 5, times dy dt, and then plus, well, all of this, which is equal to 25 times 2 times 2, so 100. So then, noting that all of this right here is equal to 0, you should be able to pretty quickly get that dy dt is equal to negative 20. Okay? All right. So that's example 1. So any questions on any of that? So I know some of you are still writing that down, so we'll give you guys a sec. I'll just do this, so you guys have an idea of what's going on. So So example 1 was the only like non-real world problem that I wanted to focus on for today. So now the next 3 examples I'm going to focus on are going to be actual real world examples. So the problems that follow for the rest of this lesson, as well as the next lecture, will involve applying related rates to real world applications. So with situations like this, it might help to abide by following 5-step procedure here. Okay? So we have 5 steps. So first step is we have to identify the needed formula if it's not already given. We have to identify which variables change and vary with time t and which are constant, and plug any constant values into the formula if applicable. Determine what values/rates are given and which we need to find. Take derivative of both sides with respect to t via implicit differentiation. And then plug in values and solve for the desired quantity. Okay? So at first you're like, okay, well that's a bunch of information that I'm probably going to forget in like 5 seconds. So let's actually apply that to an example before you forget it. So example 2, a cylindrical tank standing upright with one circular base on the ground has a diameter of 38 centimeters for the base. How fast does the water level in the tank drop when the water is being drained at 6 cubic meters per second? And note that the volume of a cylinder is pi r squared h, where r is the radius of the base and h is the height of the cylinder. Okay? So in this case, let's say, all right, well, we have a cylindrical tank standing upright, so let's draw a picture of that. And hopefully I don't screw this up. Okay. That's not bad. Not bad. 8:30 in the morning, 8:30 morning drawing is not that bad. How about that? All right, so let's go ahead and use this reasoning to see what's going on. So the first step is we have to identify the formula that we need to work with if it's not already given. Well, good news is that the problem gives us that formula. So in this case, we need to work with v equals pi r squared h. Okay? So in this case, we say, all right, the 3 variables that we need to work with are v, r, and h. So step 2 says, all right, which of the variables change or vary with time t and which are constant? So in this case, we say, all right, of the 3 variables that we have here, I'm looking at our picture here, we notice, all right, well, the tank always has a diameter of 38 centimeters for the base. So that means is that essentially we have 38 centimeters. Okay, so what that tells us is that, all right, well, of the 3 variables, which would remain constant throughout the whole process? Yeah, just the radius, right? Because this always has a fixed diameter of 38 centimeters. So in this case, that's the only variable that's going to vary with or be constant with time t. So if the water level drops, then that means that v and the volume and the height change with t, but r is constant. Okay? So in this case, the radius would then equal what, given the diameter of 38? Go ahead. 19. Just 19, right? Because all you have to do is just take your diameter and divide by 2. So we have 38 over 2, so 19. Okay. So now as a result, now that we've identified that r is always constant, it might help to plug any constant values into the formula if applicable. Well, in this case we can do that. So we have v equals pi times 19 squared h. So if you plug this into a calculator, you'll notice that 19 squared is just 361. So that tells us that we have 361 times pi times h is just equal to v of h. So what that tells us is that we can now express the volume in terms of the height h. So, so volume in terms of h. Okay? So that's step 2. So now step 3 says, all right, what are we have to look at now what we're given in terms of numerical values. So the thing is, we've already used the 38 centimeters part, so that's all said and done. And now we have to focus on how fast the water level in the tank drops when the water is being drained at 6 cubic centimeters per second. So what do we notice? So the only numerical value we haven't used yet is this 6 cubic centimeters per second. So looking at the units of this, which do you think that's going to correspond to? Would it correspond to dV dt or dH dt? Taking a look at the units. Go ahead. dt, yeah, dV dt, right? So in this case, dV dt is going to equal, so the catch with this is that even though that is correct, that 6 will correspond to dV dt, the caveat, though, is that the water level in the tank is dropping at a rate of 6 cubic centimeters per second. So as a result, that would mean that the water level is decreasing at that rate. So because of that, that should mean your derivative is going to end up being negative. So the negative accounts for water level decreases. Okay? And then from this, we have to find dH dt. Okay? So because of what we have established in 3, now we can assume that v and h are differentiable functions of t. So if that's the case, that says, all right, well, we have to take our formula here and say, all right, now we have to differentiate both sides with respect to t. So we have d dt of v equals d over dt of 361 pi times h. So then as a result, we say, all right, if we treat v and h as differentiable functions of t as in the last example, then what would the left-hand side be here?
dV over dt.
Yeah, in this case, it's just dv over dt, right? Because in this case, f of v is just v. And here we would end up with g of, in this case, h equals 361 pi h. So in this case, if we apply the same idea to this example as we did in example 1, basically you're going to end up with the left-hand side is dv dt, and then the right-hand side will equal what? So in this case, we have g of h, so now we're differentiating. We're working with the derivative of g with ultimate with respect to t here. So
361 pi dH dt.
exactly, because in this case, we have that g prime of h equals 361 pi, and then to get dg dt, all you have to do is just multiply dH dt to this, and you're done. dH dt. So in this case, you have 361 pi dH over dt. Okay? So that's step 4. So now step 5 is just, okay, now we have to plug in the given values and solve for the desired quantity. So in this case, it's pretty simple because all we have here is that dv dt is -6, so we have to find dh dt. So just plug in -6 on the left-hand side equals 361 pi dh dt. So that should pretty quickly tell you after dividing 361 pi to both sides that dh dt equals -6 over 361 pi. Okay? And just to do a quick review right quick, what would the units of this be?
Centimeters per second.
Yep, centimeters per second. Good. Okay. So in this case, this would be your answer here. All right? Yeah?
So like the question, it says how fast is the water level dropping, and our answer is negative. But like, so we're pretty much saying it's dropping at a rate of negative something.
Well, the negative accounts for the fact that it's dropping. So in this case, that says, so if we wish to write this in a complete sentence, so in this case, when water is drained at 6 centimeters cubed per second, the water level drops at rates of, in this case, 6 over 361 pi centimeters per second. So if you want to write down a complete sentence, that would be what you need. Okay. So in this case, what you'll notice is that in this case, we don't need the negative here anymore if you want to write this as a complete sentence. So one thing I will remark is that the homework on Long Capital will say do not put a negative in the answer. So in this case, if you're asked to find, all right, well, how fast is the water level dropping? In this case, you would just input this part here. You would input 6 over 361 pi. So put this in Long Capital. Okay. All right. So any questions on that? Or any other questions, I should say? Okay. All right. So we're going to example 3. Okay. Then we still need example 2. So for those that are able to take a look at example 3, what you notice is that there's 2 parts to this. But for now, I'm just going to focus on the first part because the second part is almost identical except for the formula being used. So what I'll do is say, all right, so for example 3, a spherical balloon is being deflated and its radius decreases at a rate of 1.1 meters per second. So the first part says we have to figure out how fast the volume decreases when r equals 10 centimeters. And we recall that the volume in terms of the radius is 4/3 pi r cubed. So the good news is that, well, problem already gives us what our formula is going to be in this problem. So we have 4/3 pi r cubed. So that's step 1. So nothing too crazy with that. Step 2, we have to remember, so step 2 was identify which variables change and vary with time t and which are constants. So in this case, we only have 2 variables we have to work with, so that's a bit nicer in this problem. So if the spherical balloon is being deflated, so I'm going to denote this as our balloon with radius r, then if the balloon is being deflated at a rate of 1.1 meters per second, or the radius is decreasing at that rate, then we have to say, all right, well, which of these two variables would vary with time t and which will remain constant, if any?
None of them stay constant.
Yeah, none of them are constant, because if the radius decreases, then you realize so will the volume, right? So in this case, V and R change with t. Okay? So in this case, there's no constants that we have to worry about here. So moving on to step 3, which says determine what values and rates are given and which we need to find. Okay? So we're given. So the problem gives us pretty quickly that, well, we have to focus on the situation when R equals 10. So R equals 10. So that's that one. And then if we take a look at the only other number being used here, we notice that the only other one is the radius decreasing at a rate of 1.1 meters or centimeters per second. So what would that correspond to here? So it's decreasing at a rate of, the radius decreases at this rate. So, and just dRdt, right? Okay. And then because it's decreasing, that must mean the derivative has to be negative. So negative 1.1. So accounts for R decreasing. Okay. So in this case, that tells us all we're given in terms of the numerical values. So now we have to find, well, so now what do we have to find here? Okay, now we got to find dBdt. Good. Okay, so now let's go ahead and take our formula from step 1 and then go ahead and differentiate it with respect to time t. Okay, so we have d over dt of v equals d over dt of 4/3 pi r cubed. Okay. So as per the last example, well, if we just differentiate v with respect to time t, we just get dv dt, no problem. As per the last example. But then what does the right-hand side want? Let's give someone else a chance. So what would the derivative of this side be with respect to time t? So in this case, if we again treat r as a differentiable function of t, what we can say is that g in this case of r is 4/3 pi r cubed. And we have to find dg with respect to time t, right? So still kind of harkening back to example 1 here. So in this case, we say, all right, if g of r is 4/3 pi r cubed, then what would dg dt equal here? So if we differentiate, if we just focus on this, we differentiate g of r as we normally do, then this would equal, if we differentiate g of r, then g prime of r would equal 1. So differentiate 4/3 pi r cubed with respect to r. What would that equal? Yeah?
4 pi r squared.
Yep, 4 pi r squared. Good. So then that tells us that if you want to find dg with respect to time t, then all you have to do is just multiply this by dr dt. So dg dt then just equals 4 pi r squared dr dt. So that is what will go here. So dr dt is what will go here. All right. And then from here we say, all right, now we just have to plug in our given values and solve for the desired quantity. So in this case, all we have to do is find dv dt. And in this case, we have 4 pi times r squared, so 10 squared, times dr dt, so negative 1.1. So if you plug this into a calculator, then what you'll notice is that this is just, well, negative 440 pi centimeters cubed per second. Okay? So that would be your answer to this problem. All right? Okay, so any questions on that? So, yeah, like I said, number 2 is basically, it's basically the exact same idea, except you're just using a slightly different formula. But other than that, it's the exact same idea. So, for now, we're just going to go ahead and skip that. So, actually, well, I'll just say check notes. Check notes on webpage. So that's all I'll say on number 2. So with that, we're going to go ahead and move on to example 4. Okay. Does anyone still need example 3? Okay. Good? Okay. Alright, so now let's move on to our last example. So sand is poured onto a surface at 14 cubic centimeters per second, forming a conical pile whose base diameter is always equal to its altitude. So how fast is the altitude of the pile increasing when the pile is 4 centimeters high? So note that the volume of a cone is pi over 3 times r squared h, where r is the radius of the base and h its height. Okay? So what we're going to do with this is, let's go ahead and draw a picture, because this one, there's a little bit more going on here, besides just, oh, here's a ball, here's a cylinder. So in this case, let's see what we have. So in this case, we have our good old cone, or conical pile. Okay. So in this case, we got h. Here's the height h, and here's our height or radius r. So if that's the case, that's our cone, right circular cone in this case. So in this case, we have, all right, well, 1 is already given to us again. So we have v equals pi thirds times r squared h. And that is a terrible way of writing that. Let me fix that. R squared times h. Okay, that's better. All right, so now here's something that's interesting what's happening. So with 2, like we said, we have to identify what variables are changing / varying with time t and which are constants. And like we said, we have to plug in any constant values into the formula if applicable. So if sand's being poured onto this pile here, are any of these going to be, are any of R, H, and the volume V going to remain constant?
It says R and stay equal. So
Yeah. So in this case, like we'll just so ignoring this part of the sentence right here, are any of these going to be constant? No. So V, R, and H always change with T. But like you said, there's a nice little relationship between the radius and the height. So base diameter is always equal to altitude. So in this case, we say, all right, well, if our base diameter is just this, then that says that the base diameter here is always equal to h. So d is equal to h. But the nice thing is that, well, wait a minute, the diameter is just 2 times the radius. So what that tells us is that the height is always 2 times the radius. So that's one nice thing about what this relationship here gives us. So what we can do with that is say, all right, well, we can then plug in this relationship into our formula here to get that V. So V, okay. V, there we go, is then equal to pi over 3 times R. Oh, wait a second. Before we commit to that, I just realized we need to actually look at what we're given here, because what you'll notice is that there's a bit of a nuance in what we're given here. So, because even though H is equal to 2R, and we could just plug in H into here to get volume in terms of R, there's a bit of a caveat. Okay, so given. So let's take a look at what we're given. So sand is poured onto a surface at 14 cubic centimeters per second. So dV dt is just, well, that's just 14. And we have to focus on the situation when the altitude or height of the pile is 4 centimeters high. So H equals 4. But now we have to find what? So we need to figure out how fast the altitude of the pile increases. So that tells us we need to ultimately figure out what rate here. dHdt, right. So in this case, we have to be a bit careful. So like I said, even though we could technically use this relationship to express the volume here in terms of R, that's not going to be helpful here because we need to find dHdt. So ultimately, that tells us that we need to get our volume in terms of height, not radius here. So get V in terms of H. So if that's the case, we can use this relationship here to say that R is equal to H over 2. And then so we can say, all right, now that we have the radius in terms of height, that tells us, all right, then V equals pi over 3 times H over 2 quantity squared times H. So then that tells us, well, we have pi times, in this case, H squared times H, so H cubed. And then 3 times 2 squared, so that would just be what? Yeah, just 12. So this is the relationship you're going to want to use here for number 3, or part 3. Okay, so that tells us that, okay, now we have volume in terms of height, because we need to find dHdt. So now that we have that, let's go ahead and differentiate both sides with respect to time t. So we have d dt of v equals d dt of pi over 12 times h cubed. So, as we've already seen enough times before, this is just going to end up being dv dt. So I'll say that's just that. But then, what about the right-hand side? So if we employ the similar trick that we used in example 3, then what would the derivative of the right-hand side be with respect to time t? Someone else. Sure, go ahead.
Would it be 1/4 pi h squared?
Yep. So in this case, you'd have pi over 4 h squared times, remember you're differentiating with respect to time t here.
Oh, dh over dt.
Yep, times dh dt, right? Because like I said, this is just basically harkening back to our astro school, like where we have to differentiate this like we normally do, but then because of chain rule, you have to multiply in d, in this case, h dt. So let's say, from astro school. Okay. So I'll just say differentiate pi over 12 h cubed as you normally would. Then multiply dh dt. Okay. Okay. So that's just something that we saw in the implicit differentiation lesson last time as well. Okay, so now that we have all that, now let's go ahead and plug this in back and plug our given values into our equation here to get dh dt. So we have 5. So in this case we have dv dt, which is 14, equals pi over 4 times 420 squared times dh dt. So in this case, we just have 4 squared over 4. So this case, this simplifies pretty nicely to just 4 pi. Okay. So then in this case, we say, all right, well, if we need to just get dh dt by itself, this will give us dh dt. Divide 4 pi over to the other side. You have 14 over 4 pi, which simplifies pretty nicely to what? 7 over 2 pi. Good. And this is in centimeters per second. And that would be your answer for part 5. So example 4 as a whole. Okay. And that's all I have for today. So you guys have any questions on anything? All right. Then, like I said, I'll have office hours tonight on Zoom. And yeah, that's about it. Otherwise, I will see you guys on Friday. Yep.